Welcome to this explainer. Today, we're going to completely reframe how we think about the digital world. When you picture the cloud, you probably just imagine, endless racks of blinking lights, lines of code, or massive power grids. It all feels so weightless, right? Totally digital. But today, we're shattering that illusion. We're diving into the deeply physical, rapidly vanishing resource that is quietly keeping artificial intelligence from literally melting down. We're talking about water, and it's becoming an imminent bottleneck for the entire future of computing. So let's dive right in with a pretty wild question. Does AI literally drink water? Well, yes. Every single time you ask an AI a prompt, whether you want it to write an email, generate a funny image, or summarize a long document, it takes a literal sip of water. And to put that into perspective, over the course of our time together today, the massive servers running the world's most advanced AI models will evaporate enough fresh water to fill multiple Olympic-sized swimming pools. The sheer volume is absolutely staggering, and it's firmly anchored to our real physical environment. To understand why water is the ultimate bottleneck here, we really have to wrap our heads around the sheer, mind-boggling scale of this infrastructure build-out. Right now, tech giants are spending an estimated $1 trillion on AI infrastructure. $1 trillion. That money is building massive data centers, some of them spanning millions of square feet, where they're stacking the most densely packed, high-performance semiconductor chips ever manufactured. And these chips, they're running at near maximum capacity, 24/7, basically like a car engine constantly redlining. So, the crucial point here comes down to thermodynamics. A single rack of these modern AI servers can draw tens of thousands of watts of power. And by the simple laws of physics, all that electrical energy turns straight into extreme heat. If you've ever pushed your laptop to its limits and heard the fan absolutely screaming, just multiply that thermal load by millions. If you don't remove that heat instantly, the silicon physically degrades, or worse, the systems have to shut down entirely to prevent catastrophic, wildly expensive fires. Historically, the most cost-effective way to remove heat at an industrial scale is by using water. And this really brilliantly illustrates the tension we're facing. Take Phoenix, Arizona, for example. It's a major tech hub situated smack in the middle of a desert. By 2031, data centers could demand more than 20% of Phoenix's entire annual municipal water use. Think about that for a second. Diverting a projected 20% of a desert city's water just to manage the thermal limits of corporate infrastructure, it's literally like building a massive water park during a severe drought when no one actually gets to swim. Let's look at the actual mechanics and see how this direct water usage cycle works in practice. So how is this water consumed? Well, facilities use massive evaporative cooling towers. First, they pump warm water out of the server rooms, expose it to the outside air, and let a portion of it evaporate. That phase change pulls a massive amount of heat out of the water. But as the pure water evaporates, all these concentrated minerals are left behind. So eventually they have to perform what's called a blowdown. They dump that corrosive, mineral-heavy water right into the sewer, and then they demand fresh makeup water from the city to dilute the system all over again. It is a continuous, incredibly thirsty cycle. Moving on to Section 1, the 12-by-plot twist. Let's uncover AI's indirect water footprint. You see, the visible water actively evaporating off the roof or going down the drain is what the industry calls direct usage. But that's actually just a tiny fraction of the total footprint. Check out the staggering 1:12 ratio here. This indirect usage is the water consumed miles away at the actual power plants generating the gigawatts of electricity needed to run those servers. Historically, for every 1 gallon of water evaporated at the data center, 12 gallons are consumed over at the power plant just cooling the massive steam turbines. It's a multiplier that completely catches people off guard. And this completely redefines the calculus of a green grid, showing exactly why energy sources matter so much. Traditional plants like coal, gas, and nuclear use extreme heat to boil water, create steam, spin turbines, and then require massive cooling towers to cool that steam back down. But renewables, like solar and wind, they don't use a steam cycle at all. They generate electricity silently and, crucially, dryly. So transitioning a data center to 100% wind or solar power silently neutralizes that massive 12x indirect water multiplier entirely. It's a real game changer. Section 2, Radical Liquid Cooling Tech, re-engineering the server farm from the ground up. Now, even with the power grid fixed, we still have to cool the physical building, right? Blowing cold air over racks just doesn't cut it anymore because, well, air is a terrible conductor of heat. Engineers are desperately scrambling to solve the thermodynamics inside the actual server room without evaporating millions of gallons into the desert air. So they're having to completely redesign server architecture from scratch, deploying radical liquid cooling methods.
First, we have directed chip cooling, where engineers strap macrochannel heat sinks right onto the processors. It's kind of like taking a high-performance car radiator and strapping it directly to the brain of the computer. But the second method is way more radical: immersion cooling. This involves wildly submerging the entire server rack completely in a sealed vat of liquid.
Okay, I know exactly what you're thinking. Submerging live electronics sounds like a fast track to a massive short circuit, right? But they pull off this immersion trick by using something called dielectric fluid. This is a highly engineered synthetic liquid, like a fluorocarbon or mineral oil, that has excellent thermal conductivity but absolutely zero electrical conductivity. It allows the live electronics to operate flawlessly underwater. It's basically like jumping straight into a swimming pool instead of sitting in front of a fan on a blazing hot day. And here is how they actually remove the heat from that fluid. In a two-phase immersion system, the fluid is designed to boil, but at a really low temperature, around 120 degrees Fahrenheit. The heat from the servers makes this specialized fluid boil into a vapor, which then rises, hits a chilled condenser coil, and literally rains liquid back down onto the servers. It forms this completely self-contained weather system right inside the server box that loses absolutely zero water to the outside atmosphere. Pretty amazing, right? By sealing these systems up, data centers can finally stop relying on evaporative cooling outside. However, there's always a catch. To shed the heat to the outside world without evaporation, these closed loops rely on what are called dry coolers. Think of massive industrial coils with enormous fans. The trade-off here? Electricity. Dry coolers demand massive amounts of electrical power to spin giant fans fast enough to actually move heat, especially if it's already 110 degrees outside. So you save millions of gallons of water for sure, but you significantly crank up your electricity consumption. To balance out this trade-off, the industry is getting incredibly creative. Some facilities use water-side economizers. This means strategically locating data centers near natural cold bodies of water, like deep lakes or fjords, and letting nature do the heavy lifting. Others, like a Microsoft facility in San Jose, run entirely on reclaimed, non-potable sewage wastewater from the city. They're even deploying prefabricated modular data centers, basically shipping containers filled with servers that have built-in systems to harvest their own rainwater directly off the roof. Okay, Section 3, the accounting loophole, how the industry measures its footprint. So with all this wild, incredible technology deployed, we arrive at a critical checkpoint. How do we actually verify any of this? How do we know the true environmental impact of these companies and ensure it's not just corporate spin? Well, the industry standard metric relies on WUE, or water usage effectiveness. It's a fairly simple ratio, the total water used for cooling divided by the total energy consumed by the IT equipment. The ultimate goal is to drive this ratio as close to zero as humanly possible. A low WUE indicates a facility is doing complex computations while drawing way less from local watersheds. But the crucial flaw here, the massive structural loophole, is highlighted perfectly by this quote. It points out that by omitting power plant data, companies are effectively erasing the vast majority of their actual water footprint. They're meticulously measuring the water evaporating out of their own cooling towers, but completely ignoring that massive 12x indirect power plant multiplier. It's essentially equivalent to boasting that your new electric car uses zero gasoline, while completely ignoring the fact that the power grid charging your battery is running on dirty diesel generators. It heavily skews their true environmental impact. Transparency is absolutely the necessary first step to solving this. And currently, Meta stands out as the only major player actively and voluntarily including that massive indirect multiplier in their public accounting. Tracking the water consumed by their power utility providers gives a much more sobering but accurate view of the industry's actual drain on our resources. Looking forward, tech giants like Microsoft and Meta have pledged to be water positive by 2030. What does that mean? It means they intend to replenish more water into the environment than they consume globally. But to cross this positive threshold, they have to do a lot. They must completely halt their operational consumption, using things like dielectric immersion and transitioning grids to solar. But then, because hydrology is strictly a local issue, they have to heavily fund physical, local watershed restorations right where they operate. This means actually paying to fix leaky municipal pipes or restoring local natural wetlands so they can act as natural sponges. And finally, Section 4, the future AI geography, when water physics dictate the algorithm. Ultimately, the next time you fire up an AI tool, remember that you aren't just communicating with some invisible ethereal cloud. The intelligence might be artificial, but the resources it consumes, the dielectric fluids boiling, the massive dry coolers spinning, and the enormous turbines turning, are intensely real and firmly bound to our local physical environment. So, I'll leave you with a final provocative thought to chew on. As data centers drain arid regions and fiercely compete for a dwindling supply of fresh water, local governments might stop treating water as a basic public utility. Imagine municipalities implementing real-time dynamic surge pricing for water. If a heatwave hits, the cost per gallon could skyrocket in real time, literally forcing AI algorithms to frantically route their computations to servers in colder, wetter climates just to avoid the massive bill. We are moving toward a fascinating future where the physical geography of artificial intelligence is dictated entirely by the physics of water. Thanks so much for joining us for this explainer, and keep learning.